In this video, we will explore how to evaluate the performance of queuing systems. In our exploration of queue performance, we need to address a critical factor, service time variability. This is measured using the coefficient of variation for the service time process, represented as CVP. We can calculate CVP as the ratio of the standard deviation of activity times to the average activity time. For example, if the standard deviation of activity times is 150 seconds and the average call or activity time is 120 seconds, the CVP is calculated as 150 divided by 120, giving us a CVP value of 1.25. This measure is essential as it provides an understanding of the variability around the average service time, which can impact the efficiency of our queuing system. In understanding queue performance, it is crucial to examine the time spent in the two stages of the system: time spent in the queue and time spent being served. Let's recall some of our key terms. P represents the activity time. K is the number of servers. WQ is the time spent in the queue, and W is the flow time, calculated as WQ plus P. We can calculate the time in queue using the formula activity time divided by K multiplied by the quantity of utilization to the power of the square root of 2 times K plus 1 minus 1 all over 1 minus utilization times the quantity of CVA squared plus CVP squared all over 2. This equation is good for all GGK-queues. For an MM1 model, where both CVA, arrival rate variability, and CVP, service rate variability, equal 1. The formula simplifies accordingly. However, it is crucial to note that this equation applies only to a stable system. That is, a system with utilization less than 100%. Once utilization reaches or exceeds 100%, we encounter the saturation effect, causing a dramatic increase in queue time. Decoding the determinants of queue time in a stable system, we direct our attention to the equation for time in queue, WQ, which is WQ equals activity time divided by K multiplied by the quantity of utilization to the power of the square root of 2 times K plus 1 minus 1 all over 1 minus utilization times the quantity of CVA squared plus CVP squared all over 2. There are 3 primary factors at play. The first is the capacity factor, derived as the average processing time of the system, or P over K. This factor remains unaffected by fluctuation in demand. The second component is the utilization factor, here. Average demand comes into play as utilization is essentially the ratio of demand to capacity. Lastly, the variability factor reflects the impact of variability on queue time. Keeping average demand and capacity constant, an increase in variability corresponds to a longer time in the queue. This underlines the importance of managing variability to optimize queue performance. To illustrate the application of these equations, let's consider an example where we have an inter-arrival time A of 35 seconds, an activity time P of 120 seconds, and K, the number of servers at 4. The utilization in this case is calculated as P over K times A, which equals 85.7%. We assume that both CVA and CVP, coefficients of variation for arrivals and service times, are 1. Applying these values into our equation for time in queue, WQ equals activity time divided by K multiplied by the quantity of utilization to the power of the square root of 2 times K plus 1 minus 1 all over 1 minus utilization times the quantity of CVA squared plus CVP squared all over 2. We find that WQ equals 120 divided by 4 multiplied by 0.857 to the power of square root 2 times 4 plus 1 minus 1 all over 1 minus 0.857 times 1 squared and 1 squared over 2 equals 150 seconds. Therefore, the total flow time, W, the sum of time in queue and activity time, is W equals WQ plus P equals 150 plus 120 equals 270 seconds. This means that, on average, a customer will spend 270 seconds in the system, which includes both their waiting time and service time. Due to the computational complexity, I recommend using Excel for the computation.